Hey, so today we're going to be talking about graphing and interpreting graphs. Um, and there's a bit of a premise here. So this is obviously, physics. This is AP Physics 1. But the reality is that this graphing and interpreting graphs thing is applied to anything, any science, and most social sciences like economics and psychology, and pretty much anything you can think of that does anything with statistics. So a lot of the examples we're going to be doing here um, are going to be outside of the physics curriculum, but it's still important to be able to extrapolate data from them and be able to interpret them, which shouldn't be too out of the ballpark to want to have someone able to do that. A big part of the Physics 1 exam, and actually all the AP Physics exams, all four of them. Oh, hey, we just had someone join. Hi, Ari. So I'll start over then. This stream is about graphing and interpreting graphs. And the reality is that this skill is very important in any science and almost every social science. So a lot of the examples we do today are going to be outside of the realm of physics, which I think is pretty fair because the physics exams, all four of them, all four AP physics exams rely on being able to extrapolate your knowledge to other subjects that you maybe weren't directly tested on, which I think is a good thing, to be honest. So this is almost the graphing portion is almost completely going to be a FRQ, and the basic anatomy of that is you're given a situation, a physical situation. Let's say you're given a string, or you're given a mass, and you're given various strings of various lengths. Light strings, that's an important part. So a physical situation. And the example is you're given a mass and light strings of varying lengths. And your objective is to measure the acceleration due to gravity. So obviously this example is definitely coming straight out of physics. So that's a physical situation, and then you use some math. And for this specific situation, you don't need to do any math because the formula is straight on the formula sheet. The formula sheet, or the formula, well, it'll ask you to derive an experiment using mass and light strings of varying lengths to find the acceleration due to gravity. And you're also given a stopwatch. And the whole point there is you should remember this relation. Period is 2 pi times square root L over G. That's straight from the formula sheet. And to derive that, you'd have to use calculus. So I'm not going to go through that. It's not fair to assume people watching this have calculus background. So that's the idea. So we need to create something that has a slope with g. That means we need to create something such that we have some variable, some function of some parameter. In this case, it's the length being proportional to d, being equal to some constant times gravity. Some constant times gravity. And this way, if we graph that function that we had before, f of L versus that constant k, it's not necessarily constant, it's also a function of L. I should write that. So we have f of L being some constant of L some function in terms of L times a constant g. And the basic thing we have here is if we graph that function of L versus k of L, we get a linear relation, right? That's just y equals mx plus b, where b is 0. and the m is the g. So the slope here, the slope is equal to g. So we want to find something that has g with no power on it, no square root, nothing, just g to the good old first power. And the way we do that is we're going to square both sides of the equation. We get t squared is equal to 2 pi squared, or 2 pi, 2 pi root L over g squared. And you can distribute this square. You get 4 pi squared L over g. So we have this relation, and we have something where g is, sort of this. So we can't really satisfy this relation, but we can satisfy a different relation. We have some variable, which would be a function of L, right? We have the L here, and then we have 4 pi squared L times 1 over g. So this doesn't work in our case. This k of L g doesn't really work in our case. We could do an inverse g, or we could do t squared g is equal to 4 pi squared L. And in this case, this relation does actually hold. The k of L would be t squared, and the f of L would be 4 pi squared L. But we can actually ignore the 4 pi squared. We can just look at the t squared being proportional to the length. And that should make sense looking at the formula, right? If we have t equals 2 pi root L over g, let's look in the case of 4. So let's say we have L going from L to 4L. This implies this statement is equivalent to, that's what that double arrow means. This means t going to 2t. So that sort of implication there just means you plug in 4L for L, and it spits out. We'll do the math actually. So t such that L goes to 4L is just equal to 2 pi times root 4L over g, which is 2 pi root L over g times 2, which is just 2t. So those two statements are equivalent. Those two mathematical statements are equivalent. So, and that sort of, or that's not sort of, that is consistent with what we've got here with t squared being proportional to L. Because that means L turning into something means t turning into that something times squared, or that something squared. For example, the 2t, t corresponds to L, 2t corresponds to 4L, which means that constant is squared. You could actually definitely work that out for any number n, which is nice. Any coefficient n. So that's the thing here, is we have to use some proportionality logic to do that. So the physical situation here is that we have this expression here. We'll get the constants on one side. So we have t squared g over 4 pi squared is equal to L. So that's that. And we can take some data on that. We can measure L, we measure t. So we have some set of t's. Let's say it's like 1 second, 2 second, 3 seconds, so on and so forth. We have to square that entire set, and that becomes seconds squared instead of seconds. So that becomes 1 squared second, 4 squared second, and 9 squared second. So you have to square that set and then graph t squared versus L. And don't forget label with units, like I just forgot to do. T squared is in units of seconds squared, and L will be in units of meters because it's a length. And then would have some linear line, and the slope there would be g over 4 pi squared. g over 4 pi squared. So g is 4 pi squared times the slope that you get, times the slope. And oftentimes this is literally just as easy as having a graph or you're given a set of, on the AP exam, you obviously can't like run an experiment. So it'll give you a set of data. You plot the data on a graph, you draw a line of best fit, and then you're done. So let me see if I can find some numbers online, because we could definitely work with this. Period of pendulum, acceleration due to gravity experiment. So we can get some numbers. Yeah, I don't think we can get any numbers for this. Yeah, definitely not. So the basic idea here is we'll say we have, these numbers aren't going to be right. They're not going to produce a right g value. They'll produce a g value of 4 pi squared, which isn't right. So let's say we have some data set where we did this derivation before, we walked through it, we used the proportionality logic that we were using before, and we run through the whole thing. Hi, Lawrence. Just how you doing the stream. So let's say you have some data points. You have L, it's a function of t squared. So let's say we have a length of, or we have a period, this is in seconds squared, this is in meters. So let's say we have a length starting from just 1, 2, or we'll start from 0.5. No, we'll just keep it 2. We'll keep it easy. We'll keep it in integers just to make the numbers easy. 3.0, 4.0, and then this means this is 1.0, 4.0, 9.0, and 16. So there's an important lesson to learn with this set of data. We'll draw lines. For the AP exam, it is very important that you correctly do the procedure for graphing, because you will lose points on something otherwise very easy. So the first thing that you'd lose points on is not labeling an axis. So we want to label our axes with L. Again, we have the relation that we got from the previous slide, t squared, or rather L is equal to g over 4 pi squared t squared. Make that square a little better. So we have that relation. We want to label our axes or else we lose points, and that's a bad thing to lose points on. And then we have t squared. Another thing you lose points on, not labeling the units on your axes. You want to make sure you're very clear what the units are. Meters and squared seconds. Another thing you'd lose points on, not using the majority of the space you're given. If you have a graph where you only have some of the data points plotted, or you have all the data points plotted, but they're plotted in the lower left corner of the graph and nowhere else, you're going to lose points. And that may seem stupid, may seem really pedantic, but the entire idea is that if you have to draw these lines of best fit by hand, and if you have something in a very small space, your line of best fit is not going to be accurate. As you expand the space you have, the likelihood that you commit an error is going to be significantly less. So we want to appropriately label our axes. So it ends at 16. So let's use the entire grid. Put a 16 there. See, where's the halfway line? Is that the halfway line? We'll put a halfway line there. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. I lost it. But, that looks about halfway, I believe. We'll do it this way. We'll just sort of approximate it with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we'll see how this works. 1, we have 3 between here. 2, 3 between here again. 3, 4, 5, 6, 7, 8, 9, 10, 11. We're running out of room. Now you don't have enough space to graph your stuff, which is a problem. Again, you'll get dot points for that if you don't include every point in your graph, or not every point is within the thing. So we'll do every 2. Second squared. That went away. 1, 2, 3. Yeah, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We have some extra space. What should we do with it? Let's keep on labeling it. Another thing you'll lose points on if you don't label the entire thing appropriately. And again, it's a dumb point to lose out on points on. 19. So the idea here is that this doesn't fill up the entire graph, right? But it fills up most of it, which is good. The majority of your graph should have some data point presence. And we're going to do this here. So we see that this is about a square. So we're going to see if we can do every 5 for, or rather, yeah, we'll go with every 5 for the 1. So I'll do this in blue. 1, actually, no, we'll just count because then the blue will show up on the graph and people get confused. 1, 2, 3, 4. 1, 2, 3, 4, 5. So that's 1. 1, 2, 3, 4, 5. That's 2. And we can already see that this isn't going to be all the way. 1, 2, 3, 4, 5. That's 3. 1, 2, 3, 4, 5. That's 4. And we can already see that's barely a majority, but that's still a majority, right? So we can actually work with this. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. We can work with that. So it's definitely, the axis is 2/3 of our data set, or our data set is 2/3 of the axis, which is more than good enough. So we're going to do some graphing. So you want to make sure your points are clear, and it's very easy to see which points you're using. And this will actually be a straight line, which is not going to be how your data is. That actually goes there. This will literally be a perfectly straight line just because the data is fabricated. Or rather, yeah. And then 4 goes to 2. And then 9 goes to 3. So we're on 9 right now, and that goes up to 3. And then last one, the 4 goes up to 16. So 16 goes up to 4. There we go. So now we have something that looks linear. I'd hope it looks linear, and we could draw a line of best fit to represent that. And I have the privilege of being able to draw this with a line tool. However, not a lot of people know this. The physics exams are you're actually allowed a ruler on the physics exams. That's not because you're going to be doing measuring. That's not right. It's because you're going to have to draw a straight line. If your line's not straight, you lose points. So, did I do this right? Yeah. Okay. So, what our line will look like? That's not a line. That's a box. Ended up not being a straight line. That worked out. So yeah, that's what our line would look like. The line of best fit. We'll start from here. And you don't have to worry about the line of best fit being perfect. As long as it's just right, I mean, you'll be fine. A lot of the times you'll you'll be given a leniency on calculating the slope because that's what this line of best fit matters for. So we need to find the slope of this line first, and here's an important piece. If you're trying to find the slope, don't use your data points. Only use points that fall on the line and make them easy on yourself. Make them easy points to calculate. Like, for example, this here would be 1, 2, 3, 4, 5, 4.2, 4.4, 4.6, 4.8. So doing something at 4 would be easier than doing something at 4.8. And similarly here, doing something 11 would be easier than doing something 11.5. So make them easy for yourself. As long as your line is straight, it won't matter which points you pick. You'll get the same slope. So you want to pick 2 points. And just pick any points. Pick points that fall on your coordinate axes on the actual intersections. Like, for example, this is a good one right here. Use a circle. Here's a better idea. Use a circle to indicate that that's the point. We'll pick another point. We'll pick another point that intersects on the grid lines because that's just the easiest way. How about that one? That's a good one. Now for the weirder part, you don't actually have to circle your points. But the whole idea with the AP exam is you're giving a solution to a problem, and you want the grader to know your solution like the back of their hand. You want them to be able to read what you're doing, and you want to communicate with them well. And circling your points and then saying circle equals the points I used. You're very much communicating your calculations you're doing. So we have to label this point. And we'll make this a little thicker to make it a little easier to read. So what's this point right here? So the t squared there is 3. So that's a 3. And this point is 1.2, 1.4. So we have that. And then this point, the t squared is 8 here. And then this is 2.2, 2.4, 2.6. So we want to calculate the slope of that line. The slope is just changing y over changing x, right? So we have points here. So the slope is going to be equal to, let's use the first point, the change in y, which would be 2.6 minus 1.4 over the change in x, which would be 8 minus 3.1, or 8 minus 3. And this is equal to 1.2 divided by 5, which is approximately point, I'm not sure what that is. 1.2 divided by 5, 0.24, 0.24. Is that answer right? No. Another place where you're going to lose points. We'll expand the canvas a little bit so I can work more a little with this. Make the width 1500. There we go. This is not just 0.24. This has dimensionality to it. We know that this is change in y over change in x, and in this case, it's change in L per change in the variable t squared. And this has units, delta L has the same units as L, because it's just an L minus an L. And this is meters. And then the t squared, the change in t squared, by the same logic, has the same units as t squared, which is second squared. So this actually has dimensions of meters per second squared. And that should make sense because the slope is g over 4 pi squared, and 4 pi squared is unitless. G has units of meters per second squared, so it makes sense that that happens. So that's the idea there. And this actually may work out. We'll see. So the next thing there is we have to calculate the g value, and we have slope is g over 4 pi squared from a couple of minutes ago. So we know 4 pi squared times the slope. This actually may work out really well, which is really funny because this data was completely fabricated. And we know the slope which is 0.24 meters per second squared. 4 pi times, or 4 pi squared times 0.24 meters per second squared. And plugging that in our calculator, let's see, we get approximately 3.14 times 3.14 times 4 divided by, or times 0.24. Wow, we actually got a pretty close value for data that was fabricated. We got 9.47 seconds, or meters per second squared, which is actually hilarious. So that's actually a pretty pretty good value because I just pulled that data out. Which makes sense because g over 4 pi squared is about 1 meters per second squared, so it makes, or about a fourth of meters per second squared. Just by convention. There's that whole joke that g is pi squared. It's kind of a bad joke, to be honest, but in that case, the slope is 1/4, which is about 0.24. So it makes sense. So what's the next thing? We have to calculate the percent error of our value. And the percent error, I'll merge the layers so this looks a little more right. The percent error, we'll do that calculation out here. This is a formula you have to memorize, not in your equation sheet. It's equal to, I'll move this down. Measured minus expected. Here, I'll write this smaller. We'll call percent E prefer error. It's equal to measured minus expected divided by expected. There we go. The absolute value of that, we calculate the difference between that. So in our case, the percent error for G, and we multiply this by 100%, just so the percent error is in a percent, and 100% is 1, and you can multiply anything by 1. So we'll get, and we can actually ignore the units here, we get 9.47, that was our measured, minus 9.81, divided by 9.81, times 100%. And we get this being approximately, let's see, 9.81 minus 9.47 divided by 9.81. Actually, we get a 3.47% error. And I'm satisfied with that for it being fabricated data. So that's the whole idea there. And there's some just pretty dumb points you can miss out on, and you're going to be slapping yourself in the face if you miss a point on something like that. That was just a procedure and not even a physics issue. Would be, like your line isn't straight enough, or you use your data, instead of your. Did I do that? Yeah, I did. Hold on. I don't know why the things weren't exactly linear, but you did some you use the data points to calculate your slope. You didn't label your axes with a variable. You didn't label your axes with the unit. You didn't fill up your entire space or most of your space. It's kind of a problem it'd be kind of really disappointing to miss out on stuff. Another thing you might lose out points on for not titling your graph. Say L versus, or rather, this would be length versus period squared. I don't think that's required for the AP exam, but some teachers are kind of nitpicky about that. But I mean, do what you must. Do what you have to do. This is optional. The circling is optional. Everything I put in purple is optional. Everything in red on the graph is required. The green part is required. Make sure it's straight. And the blue part on the graph, the data points, is also required. Make sure you plot every data point you're given, because if you miss out on some, your data is going to be a little bit bad, which It's not a good thing. So that's the whole graphing part. We're going to talk about interpreting graphs, and we have to go over some. First, we have to go over some. Make a new canvas here. We have to go over some preliminary stuff. We have to go over the shapes of graphs. That's very important. So there's a bunch of different graph types you'll see in actually pretty much any mathematical models. We have y equals b to the x, y equals b to the negative x, y equal x, y equal x squared. You probably won't see a cube, but just because y equal x cubed, y equal log to any base of x, and y equals 1 minus e to the negative x. That graph might look a little weird, but it's actually very useful for a lot of things. And we're going to be, let's label these models, or let's call them, let's give them a name each. So this first one is exponential growth. Exponential growth. The second one is exponential decay. Exponential decay. Exponential decay. Decay. And the second one is linear. Quadratic. Cubic. Logarithmic. Logarithmic. And there really isn't a name for the 1 minus e to the negative x. This is more like a, what should we call this? We'll call this limited growth, and you'll see why. Limited growth. That's just a random, or it's just a name that I'm giving to it. It's not, I don't think it's convention. It may be convention, but basically, what each graph's individual look like, we'll call this 1, 2, 3, 4, 5, 6, and then 7. So graph number 1. It's exactly what it sounds like, is exponential growth. An example like this would be, well, it starts at 1 actually. This is graph 1. This is exponential growth. An example would be population with a limited carrying capacity. Population with infinite capacity. This is more of a biology application, but or a geography application. But that would essentially be like a new population that hasn't gone anywhere near its capacity yet, because obviously you can't have infinite capacity. So, it's just a population that hasn't reached anywhere near its capacity. So the graph looks like it has infinite capacity because it's nowhere near its capacity in the first place. Number 2 would be exponential decay. And an example of this would be, let's see if I can find a good example for this. Exponential decay. Well, actually, population close to its carrying capacity would be a good one. Population close to capacity. Close to capacity. And the hallmark of graph number 1 with exponential growth is the function itself being proportional to its growth. And what this essentially means is y equaling k times the rate in y. I'm going to use some calculus notation here. And this essentially says the rate of change of y with respect to time. And population close to capacity, exponential decay, would just be the negative of this. Don't worry about the dy dt notation. That's not very important. It's just good to assign a formula to something. That's really the more important part. So the qualitative thing that connects the y equals b to the x and y equals k dy dt, or k dy over dt. Essentially says if you see something with exponential growth, that whatever quantity is, in this case population, is proportional to the growth of the population at that point. And for the same thing with population close to capacity, the population is proportional to the negative of the population growth. And in this case, the negative of the population growth would just be the rate at which the population is decaying. So that would be the amount of people proportional to the amount of people dying. A little morbid, but it's a good example. Linear, almost anything really. Momentum versus speed. You have a graph of momentum versus speed, and it's just linear. The y equals x. This is because p equals mv. And just like before, this has a single slope, which is m. That's a good example there. It's linear. Something cubic or something quadratic would be the displacement or the height something traverses as it falls down. So for this would be height fallen versus time. It would be quadratic with respect to time. And the reason why is because we have the expression delta y, the vertical displacement, is equal to v0 yt minus 1/2 ut squared. And this term is 0 if it starts from rest, which is what we're dealing with here. And then delta, or h, is going to be the absolute value of the vertical displacement, the height fallen, which is just 1/2 ut squared. And you can clearly see that there's a slope of g over 2. Proportionality constant be a better term there. But it's quadratic with respect to speed. There's another application, or there's the cubic one. I can really not ever see that being on the AP exam. Maybe for Kepler's law, but the idea there is something cubic with respect to time. An example of that is a dipole. Electric dipole would be, this line isn't a physical line, but something with a positive charge on one end, something with a negative charge on one end. If you know chemistry, this is called a dipole moment. Like a hydrochloric acid molecule would look like this. So negative charge, and a positive charge. The electric field actually decays like a cubic. So in this case, if you graph, let's see. So the electric field decays like a cubic. So if you graph, as with distance, so if you graph the electric field and 1/r, you get a cubic looking graph, which would like that actually. It's kind of hard to see that if you don't graph the other end, but it would look like that. I'll draw it a little better. There we go. And that is number 5. That's not a 5, that's an S. That's bad. There we go. So that's number 5. Number 6 would be a logarithm. The example for this is decibels, like how loud something is. Decibel is actually a logarithmic scale. So the amount of decibels the amount of decibels is actually equal to the logarithm, log base 10, of the intensity divided by some reference intensity. And if you know log rules, this would be log I minus log of I0, which means that this actually does have a vertical intercept. Unlike a normal log graph would not have that intercept, but because of this term, it does. It would have something that looks like that. And that would be graph number 6. This is dB versus I, or the number of decibels as a function of the intensity of the sound wave. That would be number 6. And number 7, limited growth. There's a reason why it's called limited growth. I'll show you what the graph looks like. The graph looks like that, and it actually has a limit. It can't go past. In this case, it's 1. This is graph number 7. So the hallmark example of this is air resistance. And you don't really learn the equations for air resistance in AV Physics 1. But it's this. I would actually think it's very reasonable to show you this graph. If this were velocity versus time, this would be terminal velocity, VT. And the whole idea here is that this is a proportionality statement. So its V is proportional to 1 minus e to the negative t. The actual equation would be velocity as a function of time is equal to the initial speed times 1 minus e to the negative this is a constant you can solve for times t. And this actually wouldn't start at 0. This would start here. I'll redraw it. This would look better redrawn because it actually better fits the model. Start here and then go like that. You would reach some limit. That limit is the terminal velocity in this case. So this would be an object falling under air resistance. And there's a reason why you can just take the normal equation without air resistance, which would be V equals V0 minus GT. Let's try the graph a little bigger. So what the graph would look like for the air resistance case would be this, approaching some value. And if you look at what that graph looks like tangent to that, it's like that. And for small speeds, you can see that this air is not that much. Let's say for V under this threshold, it could be any threshold. Let's say it's like 200 meters per second. Yeah, I mean the air is very small in that case, so you can actually approximate it that way, which is very nice. Or in this case, it would be plus. So that's that. That's the shape of graphs. That's a brief overview with some applications. It's good to be able to classify things with exponential growth, exponential decay. It's linear, quadratic, cubic, logarithmic, limited growth, because it's very good to be able to talk about things in terms of like an English sentence instead of math. One big thing about the Physics 1 exam is translating math to words and words to math and vice versa. And that's actually what my stream next week is on. The qualitative and quantitative translation and how to distinguish between the two. So the next part of interpreting graphs would be how area under curves and slopes of graphs and instantaneous versus average rates of change relates. So a lot of things aren't idealized in physics, right? Like for example, with the terminal velocity here. I'll draw the example again. You can't just find the displacement by doing VF times t, or change in velocity times change in time. Displacement in this case, delta y is not equal to delta v times delta t. Even though you would think it is, it only takes place for constant speed, and this is very clearly not a constant speed. The actual interpretation here is this is, let's say this is some value, or this is some interval delta t. Here, I'll draw this. Delta t. The actual way you do this is find the area under the curve, which is a little unsettling for some people. Here, I'll have to shade this in with the highlighter. Do I even have a highlight? This tool actually? Wow, I don't. I didn't know that. So the actual displacement would be this area, the area between this curve and the time axis. Delta y is equal to area. And the reason why is because essentially, like the you can approximate each small delta t. Each delta t becomes smaller and smaller and smaller, and then finding the product between. So in that case, small change in t would be dt, and in that case, a small displacement is vdt. That's what the d means, by the way, from before. And for small delta t, that would be the area of this rectangle. And essentially, you sum them all up, and as the delta t gets smaller and smaller and smaller, those rectangles approach the actual area of the graph. So you find the area. A little more common example that I think is more fair to be given would be like you're given a v of t graph that, let's say, looks like that, and then you have a semicircle with some known radius, and that's it. That'd be the graph. This would be v as a function of time. Let's say this height right here is 5 meters per second. This width right here, or this value would be 6 seconds. This is 9 seconds, and then this is, I don't know, 15 seconds. And then this height right here, between the top and the bottom of the circle, this difference, let's say it's 2 meters per second. The idea here is that to find the displacement, you have to find the area under this entire curve. Hi, Alvin. Just saw you doing the stream. So again, the idea here is we find the area. So the first thing is an area. This first segment is a triangle. So an area of a triangle is 1/2 base times height. So in this case, it would be 1/2 times 5 meters per second times 6 seconds plus the height of the rectangle, which would be 3 seconds times, I didn't give a time here. Say it's 3 meters per second. Or I didn't give a speed there, rather. That'd be 3 meters per second times 3 seconds. And then we have a semicircle here, and this area of a semicircle is 1/2 pi r squared, and we know r is just 2 meters per second. So it'd be 1/2 pi times the radius squared, which would be, no, it doesn't seem right. Yeah, it's not right. You couldn't, no, never mind. We're gonna ignore the semicircle part. Because it's kind of weird in its own little way. So we're gonna ignore this portion. Because a semicircle geometrically is not going to necessarily have that same area. So let's be equal to, let's see, 1/2 times 30 meters plus 9 meters which is equal to 15 meters, plus 9 meters, which is equal to 24 meters. So that's that. You'd have to find displacement that way, not by just doing delta v delta t. And instantaneous slopes versus average slopes. So I'm going to build up the idea here. Let's say we have some function as a function of x, looks like that, and we want to find the average rate of change over some interval from, let's say, 0 to 1. So that would just be the slope over that interval, the average rate of change. So we want to find the slope of that line. I'll make it a different color. Purple is good. Purple's a fun color. So the average rate of change would be the slope of that line, which would be f of 1 minus, well, in this case, f of 0 is 0 over 1, which would just be f of 1. But what happens if we shrink that interval? If we shrink that interval, let's say we're shrinking it closer to 1, I'll try my best to recreate that graph. So it's pretty good. And we shrink that closer to the interval closer to 1. Let's say we do it right here. And we construct that line. And we compare that to the slope of the line tangent to the graph at that point. What you should notice is, rather, I'll do it up here, because me recreating the graph isn't a good idea. Let's say we wanted to find the slope from a point closer. It would look like that. And then when we look at the line, the slope of the line tangent to the graph at that point, it would look like that. And what you should notice is that, make that pink. What you should notice is that the slope of the line tangent at that point is getting closer and closer and closer to the average slope as you decrease that interval. First it was from 0 to 1. Now it's from, let's say this is 0.8 to 0.1. That's not a paintbrush. Say this is 0.8. And the idea is that the average slope over, if we make that interval close to 0, so small that it's immeasurable, the average slope over a 0 interval, the average slope over 1 point is just the instantaneous slope of that 1 point. And it becomes the slope of this tangent line right here. So that's the idea there. So in terms of physics, that would mean if we have displacement as a function of time, and let's say this is some weird looking graph, we could find the velocity, the instantaneous velocity at any point on this graph just by finding the slope of the line segment, which is very useful because that means you can find the speed at any given point, which is very important and very physical. And in the same way, we can take a graph of velocity versus time, and we could do something really cool. So the slope here is probably here. This is the same graph as this. So the slope here is probably -1, and then it's 0 for a bit, and then, or rather, it's +1 for a bit. Then it's 0, and then it's -1 for a bit, and then it's 0 again, and then it's +1 for a bit, 0, and then +1 for a bit. And basically, you can see that there's no acceleration going on in this graph. And there's also the same case here, is that if you have, say, acceleration, it's a function of time. We'll do the weird looking graph again. This area is the change in speed. So a quick little summary of that. I'll just expand my canvas here. So a quick little summary of that is we have A V, and displacement. You go from A to V by doing an area. You go from V to X by doing an area. You go from X to V by finding a slope. And you go from V to A by finding a slope. And it should be a little intuitive, at least maybe not now, but at some point in your life, it should be a little intuitive just because, it's like the X to V and the V to A with the slope should be intuitive just because it's a rate of, that's X going to V, that's V is the rate of change of X, and slope is a rate of change. And same with acceleration. Acceleration is a change in speed, and a change in speed is a rate of change, and slope is a rate of change. So, and the area is just the inverse of that rate of change. So that's that. I really don't have anything else. We'll do a quick little experiment just to showcase how weird you can get. Let's say we wanted to find the accelerator, or we wanted to find constant big G. We're given a space station that can just go up and down, and one string and a mass. So first thing we have to do is find the acceleration due to gravity as a function of height. And this is the first thing we need to do is find the acceleration due to gravity. So mg is going to be g m, mass of the planet, over the distance from the center of mass. So it's the radius of the Earth plus the height squared. I'm doing this quick because we don't have a lot of time. So therefore, g as a function of h is gm over r plus h squared. So we have the period being, you'll see that the radius of the Earth actually doesn't matter in the problem. With graphing, we have t square root L over G, again, straight from the formula sheet. And we can plug stuff in. And when we're dividing by something that's a fraction, we can multiply it by its reciprocal. So that would be square root of L times the reciprocal of the G of H we got before, R plus H squared over big G, big M. We can pull the R plus H out, 2 pi square root L over big GM times R plus H. And distribute that all. We'll see it's 2 pi R root L over GM plus 2 pi H square root L over GM. And the thing to notice here is that this term is just a constant. This will just give you a slope on your graph, right? You'll have t as a function of h, and the intercept here will just be it'll just be 2 pi r square root L over GM, and then the slope of this graph will equal 2 pi square root L over GM. So you can actually use this experiment to solve for both the acceleration due to gravity and or you can solve for the mass of the sun. You can solve for the radius of the Earth, or the mass of the Earth. I mean, big G, the radius of the Earth, all that good stuff. You just this would be just a number, and this would also be just a number. So if you know either G, M, or R, if you know two of them, or rather, you actually need to know one of them. Then you have two equations and two unknowns, which means you can solve for both of the unknowns by algebraic system of equations. If that kind of flew over your head, don't worry. It's just kind of a novelty thing, because obviously that experiment can't happen. You're not going to be given a spaceship to do that. I was tapping my phone here. So, my Instagram here, so you can add me. Or not add me. That sounded like an old man. Follow me and DM me. Jeffries, JEFFRIES 12. You can DM me questions. The reality is that I was good at physics, so a lot of the struggles that you guys have, I never had, so I don't know whether to teach them or not. So, and I forgot to do this, but like if you DM me something, I can very quickly answer it, and I can put it on a study guide and focus more on a study guide if I know people are struggling with it, because I don't know what people are struggling with. I'm not in high school anymore, so I don't talk to people who take AP Physics 1 that much. And you can also just DM me anything STEM, stats, calc, bio, chem, physics, especially. I hope so. And you can't DM me computer science questions. I can't answer them, but I can refer to you a guy that can. But you can send me stuff, and I could answer questions for you and clear up some concepts and help you with homework. Not sure if you're still in the stream, Alvin, but if you are, have a good night. And people watching the replay, have a good rest of your day, or have a good start to your day if you're just doing it. And I hope you learned something.